Alright, welcome to the last video in the chapter, video 10.9. Here we're going to focus more on the properties now and structures of those different types of solids. Lots of objectives here, but just practice on trying to see how they all work and try to make sense of all of them. Here we go. Make sure you can describe lattice energy, or describe crystal lattice structure of ionic compounds and their properties, the bonding and properties of molecular solids, the electron C model for metals, define and classify alloys, look at the carbon and silicon elements and how they bond differently, and lastly look at the group 18 solids. So let's get going. So really just going to focus on this one page here. Not as much to write down perhaps, but really pay attention to what's going on. So first of all, we have two different types of solids. You have your regular arranged amorphous solids like glass, or you have your crystalline solids, which we're going to focus most of our time on. So again, no regular arrangement, amorphous, without shape, and crystalline, nice regular repeating arrangement. Crystalline structures oftentimes look like this. So this is your crystalline structure idea here. That's the crystal lattice. And you have different things at those different points of lattice. What's going to be there, whether it's an ion, a molecule, or what else am I missing here? Atomic, atoms. Okay, let's kind of go through and break them all down here. So let's focus on ionic first. So if you had ions at the points of crystal lattice, kind of like this picture right here. Here we got sodium and chloride alternating positive negative ions at the points of lattice. So it's an ionic compound. You know you have an ionic compound when it's a metal and a nonmetal. And a good example would be like sodium nitrate or ammonium chloride. Whenever you have two positively and a negatively charged ion, you have an ionic compound. Ionic bonding holds all those ions together, and ionic bonds are strong, which leads to the first few properties listed here on your sheet. That's why ionic compounds are hard, which means they don't scratch easily, and they also have high melting points and boiling points because of the strong bonds between them. So strong bonds indicates those properties. Ionic compounds do have a property of being brittle. That's actually given by this picture here. If a stress is applied to this and the whole thing shifts over right along that line there by 1, now you line up like charged things, like these two are going to repel each other, those will repel each other, these will repel each other, and so will that. Basically it's going to fracture off or cleave right there, and that's called being brittle. So although ionic compounds have strong bonds between all of the ions, if a stress is applied just right, it can cause things to unalign or misalign, and then repulsion forces take over, and that's why things break. Also remember that ionic compounds are good conductors of electricity, but only if they're dissolved or melted. And that's because once these ions are free to move around, like sodium positive ions are free to move around in a aqueous solution of salt water, or if you melt the salt into a liquid, so now the ions actually can flow. As long as the ions can move, that's why they can conduct. So they actually don't conduct in their solid state. And that's the ionic compounds. If the points of crystal lattice now are the molecule, so if you have molecules at each of these points of crystal lattice, now we have molecular solids. So typically molecular solids are when you have nonmetals only, all bonded together. So here we have water, carbon dioxide, oxygen. Here we have glucose. These would be considered molecular solids because they're at the points of lattice. Now it's not full out bonding holding these guys together. It's intermolecular forces holding the different molecules together. So intermolecular forces hold the molecules together, and they are generally weak compared to bonds. And those weak IMFs lead to these properties: lower melting points and boiling points. They're soft. Usually we can scratch them with like our fingernail even. They're easy to scratch. And they are insulators because when you dissolve molecular compounds into individual molecules, remember individual molecules don't have a charge, so they cannot conduct electricity. Okay, so that's the first type. This was the second type. Now we're going on to the third type, which under atomic we have the third type here. Here's the fourth type. Here's the fifth type. So if you have atoms at the points of lattice here, so these are all atoms now at those points there, they're called atomic solids. If those atoms are all metals, then we have what we call a metallic solid. So example would be like pure copper, pure iron, or maybe an alloy, which is a mixture of metals and maybe some nonmetals. Metallic solids are held together with what we call the electron C model, or the C of electron bonding. So bonding for metals is called the electron C model. And the electron C model is kind of given by this diagram right here. Basically, the metal cations are held together by the sea of valence electrons. So, if you look at sodium here, and that should be a 1 right there, I think it is. Okay, basically 3s1 is the valence electron. That is going to be contributed to electron C, which is kind of like the grayish region here, where the electrons are free to move anywhere in this gray region here. And then what's left behind is the sodium ion, Na plus metal cations. Those are these spheres here. So these are not these aren't positively charged like protons. These are actually like the cation, like Na plus cations here. So they're still in their crystal lattice here, but now everywhere around the atoms is the delocalized electrons, which can move, and that's called the electron C. Because those electrons can move, that gives rise to being very good conductors of heat and electricity. Metallic solids do have varying melting points, and their hardness can vary. Some are soft, some aren't. But basically, the big property of metals that they can conduct because the electrons can move. Don't forget that metals also have the property of being malleable, and ductile, which means you can hammer them into a thin sheet or pull them out into a thin wire. And that's again because this electron C, it kind of glues the atoms together. So if they were to be hit by a stress, rather than like breaking apart, they would just dent, but they would stay together because the electron C glues them together. Also going off metallic solids, we also have alloys, mixture of elements with metallic properties. And there's two major types. There's called substitutional and there's interstitial. Substitutional means an atom, usually metallic, an atom of similar size replaces or substitutes. Similar size substitutes. So as you take a look here in this picture here, this black element, whatever it is, it's of similar size to the white one, and it basically replaced it in the alloy. So now there's been replacement of metal atoms. Over here, interstitial means fills tiny holes. Tiny holes. So if you look at the previous picture here, there's these tiny little holes right here, and so forth. If we can find some atoms that actually fit inside those holes there, interstitial alloys are when we find atoms to fill in those tiny little holes right there. So that's the difference between the two types of alloys, substitutional versus interstitial. Okay, now backing up all the way to atomic solids here. So again, if we have atoms at the points of lattice, it's atomic. We just talked about metallic ones with metals. Now we're going to talk about a very unique one, which is the covalent network solids. Your big elements here are carbon and the silicon ones, or silicon compounds with oxygens here. We call those like the silicates. So carbon and silicon do a good job of actually making a huge, large molecule, like diamond, graphite, coal, quartz, mica, etc. Covalent bonds now are holding together all the atoms in this molecule. So, for example, if all of these things are covalently bonded together now it's basically one giant, large molecule. And that's what a covalent network is. So if you think about a diamond or graphite, really the entire thing is held together with covalent bonds, and you are technically looking at a molecule. A diamond is one giant molecule of carbon atoms bonded together. Diamond looks like this right here. Every carbon is in a tetrahedral arrangement and bond together tightly. And it's very hard, very high melting point. If you look at the one over here, this is graphite now. Graphite is layers, they're planar layers, as you can see here, it makes a plane, held together like little hexagon rings of carbons. And then each layer is IMF'd to the next layer, intermolecular forces, to the next layer there. And again, each sheet here is completely held together with covalent bonds. That's why we call it a covalent network. The entire structure is held together with covalent bonds. And again, typically they have pretty high hardness like diamond does, usually pretty high melting points and boiling points. And insulator, actually some can actually conduct pretty well like graphite can. And we'll look at that maybe a little more in class. The last type of atomic solid is when you have group 18, the noble gases, Ng here, the group 18 noble gases as solids. The only thing holding them together is really weak LDFs. They only happen at very low temperatures. That's why they have really low melting points and boiling points. These ones are not very practical, but they technically can exist if we go to very low temperatures. And the last group of solids we have then is these guys at very, very cold temperatures. And that's it for 10.9. We'll try to practice a little more of this stuff in class to learn the properties that are associated with the 5 different types of solids.